Good afternoon, everyone. Welcome to our second ISEN physics seminar session of this year. Today, it is a great pleasure to have Macarena Lagos from Columbia University. She's currently a postdoc at Columbia University, and she did her master's degree at Pontificia Universidad Católica de Chile, and then a joint PhD between Oxford and Imperial College in the UK. After that, she made her first postdoc at University of Chicago, and now is at the University of Columbia. She is an expert in scalar tensor theories of gravity, modified theories of gravity, and currently has been doing some very interesting work on gravitational waves. And today is going to talk about interacting gravitational waves. Please go ahead, Macarena.
Thank you so much for inviting me. And yeah, the idea is to tell you how we can test gravity, but focus on cosmology using gravitational waves. In particular, I'm going to be focusing on testing the matter content of the universe. So trying to see if there are additional particles or fields interacting with gravity that may leave some imprint on gravitational waves. So let me just start with some introduction. So just an overview of the current status of our cosmological model, which is the lambda CDM model. And as a phenomenological model, it works very well in the sense that it has a small number of parameters that can actually feed a wide range of data, mainly from galaxy surveys and the cosmic microwave background. And this current data tell us that this is the distribution of the energy in the universe today, where we know that only about 5% of the energy is contained in the regular, ordinary matter, and all the rest would be composed of these dark matter and dark energy components. And from a theoretical point of view, of course, this poses us a big challenge because we don't know yet exactly what's the origin and the exact behavior of these dark matter and dark energy matter contents. So the goal is trying to precisely test the different behavior that these components could have. And mainly in my case, I'm going to be thinking of dark energy. So in the lambda CDM model, dark energy is described by this constant energy density, but that may not necessarily be the case. So maybe dark energy is described by some dynamical field that maybe it evolves very slowly in time right now, but it could be something that has dynamics, that interacts with gravity. And the overall idea is that we want to test the cosmological scales in order to understand this dark energy component. Now, when we say test cosmology or test gravity, we basically, in practice, we want to compare how various models feed the data and see what the data prefers. So we already have the lambda CDM model as one possibility. And in the literature, there has been a variety of alternatives that here I also call modified gravity, but most of these modifications really modify only the low energy regime of gravity that affects cosmology. So I'm going to be using kind of interchanging these names, modified gravity and modified cosmology, to refer to the same thing. But so this figure is trying to show the various possibilities of how you can deviate from general relativity, which is the basis of lambda CDM, to obtain eventually some modified cosmology. So just to mention a few, I don't want to focus on any one in particular, but just as an example, you as a starting point in lambda CDM, you have general relativity, which is the theory of a massless spin 2 particle, which is the graviton. And one modification that you may consider is what if the graviton is actually massive? So this is one example that is called massive gravity. And that's going to change the behavior of gravity. And if this mass is very light, then it will affect the cosmological behavior, the low energy behavior of gravity. There are also, for example, this whole category here in which you can add one extra field, extra particle in the universe. And this field could be anything. It could be like a scalar, a vector, a tensor, and it could have different interactions with itself and also different interactions with gravity. And these are the various, sub cases that are here. In modified cosmology, typically this additional field is going to represent dark energy. It's going to represent some dynamical dark energy field. So certainly if we want to test cosmology or gravity, we could start going one by one across all these theories and try to see whether they actually describe or current observations or not. But of course, that's very inefficient. So here, what I want to do is take a more agnostic approach, not focus on any specific theory here. Instead, try to describe as generally as possible the modifications that your observables could have. In my case, I'm going to be thinking of gravitational waves. We're going to introduce a free parameters, and the idea is that each one of these modified gravity theories are going to correspond to specific values for these parameters. But in general, we're going to keep them free and let the data or the observations telling us what they actually are. So let me then just focus on gravitational waves. This is going to be our observable, and what we see, what we detect is the strain as a function of time. So these gravitational waves, as I'm sure most of you know, these are oscillations of the space itself that are usually only going to be visible if they are generated by very massive and very extreme objects in the universe, like black holes. And the typical scenario that we're going to have is a binary system of black holes that they are bound gravitationally in this orbit, moving around each other during this in spiral phase. And due to their motion and their strong gravity, they're going to emit a good amount of gravitational waves, and they're going to lose energy because of that. So this orbit is going to shrink due to the loss of energy until they eventually merge and form a bigger object at the end. And in this whole process, there's going to be some emission that here we're going to, in a compact way, describe by the strain. Specifically, the strain is just a particular way in which the two polarizations of gravitational waves interact with your detector. But generally, we're going to see these oscillations. The amplitude, of course, describes what is the amplitude of the distortions of the space. And the locations of peaks and troughs. We're going to analyze the entire phase evolution here of the signal. And as you can see, also these oscillations, the frequency normally is going to increase here as the binary system evolves towards the merger. And that frequency evolution is also something that we're going to observe. So just to summarize, typically we're going to look at the amplitude, how it evolves in time, the frequency, and we're going to even focus on what is a specific location of these peaks and troughs, so contain some phase information of absolute values. So we already have, from LIGO and Virgo detectors, about 90 of these gravitational waves coming from these binary systems. Now, Kagra is another detector in Japan that is going to join the network. So they're going to start observing maybe at the end of this year. Right now, they're all in pause. And now we look further down in the future. So now in the next decade, the 2030s, we're going to have other kind of ground-based detectors, such as these two, and even space-based detectors like LISA. And overall, we could be having 1 million of these gravitational wave detections detected in a single year. So the hope is that we're going to extract, as much information as possible to test cosmology. Now, normally when we talk about cosmology, it's kind of strange to think of gravitational waves. Normally, we would prefer to use galaxy surveys or some cosmic microwave background observation, and definitely that is something that will be done, and it's currently the standard way of testing cosmology. But gravitational waves can be used as a complementary probe to obtain even stronger constraints, or even some independent test to corroborate the constraints that are already obtained through the standard electromagnetic probes. So how are we going to test cosmology? That's going to be through the propagation of these gravitational waves. So they're going to be emitted by these black holes. There's going to be some high energy physics determining the emission process, but then they're going to propagate over cosmological distances. And in that propagation is when they're going to be sensitive to the expansion rate of the universe, to possible, dark energy components, and whatever other cosmological particle could be present. So from now on in this talk, I'm just going to focus on what we would observe if the propagation of gravitational waves was modified, assuming a certain emission process. So we're going to divide, the whole thing into two parts: the emission process, that I'm going to assume that it is not modified because I'm not introducing modifications in the high energy regime of gravity, and instead we are only going to have some modifications during propagation. So how do gravitational waves propagate just in general relativity? Well, if we actually look at the propagation of waves in a perfectly homogeneous and isotropic expanding universe, so we ignore inhomogeneities in the universe for now, and it has a very simple equation, which is this: that it looks like a simple damped harmonic oscillator. So here we have HP, that is our gravitational wave field, where P is a subscript that I add to describe the two different polarizations that gravity could have, but actually the equation here is the same for either polarization. Eta here is the cosmological time. This curly H is the Hubble rate, the expansion rate of the universe. Here C is the speed of light, and K is the wave number. So we're going to think that we have a single monochromatic wave, and how is it going to propagate? And from here we see very simple properties. One is that gravitational waves propagate at the speed of light. They also suffer some amplitude decay due to the expansion rate of the universe. So this we can see here from this kind of damping term that is here in the middle. And also both polarizations of gravity are going to propagate exactly in the same way. So these are like the summary of properties in GR. So now what if we had a modification of gravity in the low energy regime, like in the previous examples that I said, either in massive, you have a massive graviton, or you have an extra field interacting with gravity. And in general, I'm gonna summarize the modifications into three effects, that we see here in blue. One is this alpha M parameter that for now we're gonna keep free as a free parameter, but as I said, specific theories of gravity will predict specific values. And this alpha M parameter, as you can see here, is in the damping term. So in general, it's a friction term. It modifies how much the amplitude of gravitational waves decay. So for example, if gravitational waves are interacting with an extra dark energy field, maybe they lose some energy towards that dark energy field, and their amplitude decays faster than it would decay in lambda CDM. So it's a friction term, and there are already some constraints. So this is, as you can see, it's a dimensionless parameter. so far it is known that it has to be smaller than 10 to the minus 1 number, and there are some constraints only with this paper shows combined constraints using electromagnetic cosmological data and gravitational wave data, and that is what gives this best constraint. This other paper, in case you're interested, is a constraint that you could obtain only with gravitational wave data. That can also be done. It is a little bit worse. But the hope is that in the future, if we keep combining electromagnetic and gravitational wave data, this constraint will improve by at least 1 order of magnitude. So this
Macarena,
is one of the, yes.
Before you go on, can you tell a little bit how do you obtain this general equation before adding some friction or extra terms? How do you get this equation for the polarization mode? It's to linearizing around the cosmological metric?
Yes, it's just linear perturbation theory around a perfectly homogeneous anisotropic background.
Okay, so in principle, what you do is basically to perturbate the spatial part of the metric, or
yes, these gravitational waves are only described by the tensorial part of the metric. That, yes, it would correspond to the traceless transverse part of the spatial metric.
I see. Thank you.
Yes. Okay. So this was the friction case, and now another modification that we could get here is this alpha t parameter that would affect, in general, the propagation speed of gravitational waves. So that's why it is called the tensor speed excess. And here I have said that this alpha m and alpha t are some parameters. So implicitly, probably you're thinking that they are constants, but they're not necessarily constants. They could actually evolve with cosmological time. So if these modifications appear due to some dynamical dark energy, so there is some dark energy density that evolves in time, then these parameters could have a cosmological evolution depending on that. And particularly this alpha t could even depend on the wave number itself, k, in which case it would change the entire dispersion relation of gravitational waves. And I'm going to show in the next slide an explicit example of that. But currently, again, the best constraint is obtained mixing gravitational waves and some electromagnetic information. And it is, if this alpha t parameter is, for example, just a constant, then the propagation speed of gravitational waves can only deviate from the speed of light by this 10 to the minus 15. So they have to propagate at a very close speed.
Macarena?
And in the future, yes.
Sorry, so you are considering waves propagating in a homogeneous anisotropic spacetime. So how can you distinguish between a wave emission from a merging star, for instance, from the primordial gravitational waves? I mean, is any way to distinguish a priori?
So let's just think of general relativity. So we already, or the standard cosmological model. So the gravitational waves coming from a merger of two black holes has a very distinct shape, which is the one that I showed here in this slide. So it's always going to look like that with some, extra variations, but more or less it always has like a growing amplitude, growing frequency, and all that. Which is, and of course, it's a signal that, at least for current detectors, it's only going to last a few seconds. It's like a located in time signal. So that is something that is different from primordial emission. I guess you're thinking of inflationary emission. So inflationary or primordial gravitational waves would have different properties. So these are These astrophysical gravitational waves are transient signals that appear and disappear quickly and have a very distinct shape. So that's how, by receiving something like this, we already know immediately that comes from a merger of two black holes.
I see. Thank you.
Macarena, may I ask you something?
Yes.
So you are perturbing around an isotropic and homogeneous space-time, but
Yes.
are you assuming that this space-time is solution of your modified gravitational equations or not in this case?
Yes, in principle, yes. I mean, for consistency, yes. However, I haven't said anything. I haven't said much about the background, only because many of these modified gravity models can actually predict a background evolution of the universe that either looks exactly like the lambda CDM one or very close, like indistinguishably, at least for current data. However, for when you study perturbation theory around that background, the perturbations can really differ, even though the background can be the same. So that is why here, I'm just assuming that I have a background that looks like lambda CDM. There's nothing special about it, but still at the level of perturbations, I could have something observable and distinguishable.
Yeah, I agree. Thank you, Macarena.
Okay. Yeah, thanks for all the questions. I'm like skipping a lot of things, but and I don't know like exactly what is implicit or not. Okay, so we were here talking about this other modification that could come from, again, let's imagine some dark energy field that is interacting non-trivially with gravity. And that could modify the propagation speed, because this extra field could act in a way as a medium where the waves propagate. And the LIGO-Virgo collaboration has put this very strong constraint that without any gravitational data, this constraint would be extremely weak. Like here, instead of 10 to the minus 15, we would have 10 to the minus 1 or 10 to the minus 2. But this is one example in which gravitational wave data can improve a lot, because it does contain a different information compared to the standard electromagnetic probes. So finally, another effect that could happen is that there are additional tensorial fields, cosmological fields, that interact directly with or gravitational waves. So here I'm just calling the extra field psi, just some generic name. And these interactions is mainly what I'm going to be discussing, because it's like the less studied feature in the literature so far, at least for this friction and speed propagation. There are many groups and papers that you can look for if you're interested in. But these interactions are less well known. So how do gravitational waves behave and propagate if you have an additional tensor field interacting? But just to summarize, when we have modified gravity, the propagation of gravitational waves could change due to some friction, due to a change in the propagation speed, and possibly some dispersion relation if this alpha t depends on the wave number k. And there could also be some energy and momentum exchange with additional fields. So as I said, I'm going to focus here on the interactions, but before doing that, I want to talk about this modified dispersion relation. And the motivation is because when we have extra fields interacting, as a consequence of this energy and momentum exchange, we're going to find that most of the time, that's going to lead to a modified dispersion relation for gravitational waves. That's going to be a consequence. Yes.
Excuse me. I think you have, you said we have here additional fields, right? So I think we have a effective energy tensor, which is conserved. That's right. So you have a effective energy momentum tensor, and that is conserved. But if you take each one in the separated way, it's not conserved, right?
That's correct. So among them, they can exchange energy and momentum, but the total is conserved. Yes.
Good. Thank you.
Okay. So in the next slide, I'm going to show you then what would a gravitational wave signal look if we had only alpha t. So there's no alpha m, there's no interaction with an extra tensorial field, but there could still be a modification alpha t, where alpha t depends especially on k, on the wave number. So to start illustrating what a modified dispersion relation can do in your signal. So let's just look at let's say there's some alpha t that is non-zero. So in that case, you can write a modified dispersion relation like this, where omega is the temporal frequency. And for concreteness, I'm going to assume an example that is mentioned a lot in the literature, which is the case of massive gravity. So if we said gravity is described by a massive spin to particle instead of massless, then you would find a modified dispersion relation that is like this. It has, compared to in general relativity, we have only omega squared equal to c squared k squared. But if you add a mass, you have this extra term where mg is the mass of the graviton. And here A is the scale factor of my expanding universe that I'm adding here, to describe the realistic expanding universe. This is A. So if m is 0, we have a massless graviton, and we recover a trivial dispersion relation like in GR. But if it's non-zero, let's say that is some small mass, then we can actually write down the group velocity from this dispersion relation for waves that have this mass with a small mass. And we would find that this group velocity is approximately this. And here I want to mention two features. One is that the group velocity is going to be the speed of light c minus some positive terms. So gravitational waves always propagate slower than the speed of light, which is what we would expect for this massive particle. But the most important feature here is the fact that this correction term depends on k. So this is a dispersive group velocity in which higher frequency waves propagate faster than lower frequency waves. And that is the feature that's going to introduce distortions in your waveform. So let's look at this plot. I know there's a lot of lines, but let me take you through it. So we are simulating what you would see if you had two black holes of equal mass merging and you detect some signal. So this is a strain again as a function of time, which is what we normally detect. Here I'm going to assume that there's no modified emission process. So the emission gives me a waveform that is exactly what I would expect in general relativity. But then during the propagation, there is this modified dispersion relation. And in gray, the gray line is what you would detect in general relativity. So if there was no modification at all. And the gray line is here under the blue one. They're pretty indistinguishable, where blue is what you would detect if you had a small mass of order 10 to the minus 23 electron volts. And at least there is a difference, but by eye, we cannot really see it. But what we can see is, we detect a typical signal where the amplitude is growing as a function of time. Also, the frequency is growing. As I said before, the first oscillations that we normally detect here come from the in-spiral process of the merger. And that part has a lower frequency waves compared to the part here of the merger. So the frequency usually grows as a function of time here. And that is precisely what's gonna give me distortions with this modified dispersion relation. So now in orange, you can see that if we had a larger mass of the graviton, 10 to the minus 22, then we would get something, this orange thing that definitely looks different to gray, where you see that the wave has squeezed the signal. And this is precisely because these first few oscillations correspond to waves that have low frequency, and they propagate slower. So they take more time to arrive to our detectors, so they arrive here later. And this is what is going to cause this squeezing. And then for green is a more extreme case in which if the mass is even larger, these first few oscillations that are low frequency could arrive here, could arrive so late that they arrive even after the signal that was emitted at the moment of the merger, that was produced after. So here you can clearly see that a modified dispersion relation induces some visible distortions. And for all the 90 gravitational wave events detected so far, we have never seen anything like green. So we should already be able to put some constraints only using gravitational wave data and nothing more. And this is indeed what has been done by the LIGO-Virgo collaboration. So this is the bound. The mass of the graviton has to be smaller than order 10 to the minus 23. So basically it's close to the blue line, where here by eye, you indeed don't see anything. But a very important feature of these propagation distortions is that these distortions accumulate with time with propagation. So if a wave has been propagating for longer, it will suffer more modifications than a wave that has been propagating for a shorter amount of time. So in this example, I actually fixed that the source was always at a given redshift, at a given distance, z = 1. But in the future, we will detect gravitational wave sources that may be at redshift 10 or even further. So those gravitational wave signals that come from sources very far away will help us improve this this constraint on the mass by a few orders of magnitude. So this is very distinct to what you would expect from a modification during the emission process. That, sorry, I think I pressed some things. Okay, here we are. So if you had a modification during the emission process, you would expect all of your sources to have the same amount, all of your gravitational wave events to have the same amount of modification. But for these propagation distortions that have some cosmological origin, that is not the case. The further away, the more distortions you would expect. Okay, so now let's talk about interacting gravitational waves. So we have an additional tensor field interacting. So this is the equation of motion for general relativity, as I showed you before. And now we want to add one extra tensorial field that is going to have a coupled equation of motion with H.
Macarena, may I ask you something regarding the last point that you were pointing out regarding the emission? If we assume that the modification of gravity is at the level of the emission, I agree with you. So the cumulative effect will be can be appreciated in principle from a point of view of the detectors, or not? Is it this correct? Can I detect a modification of gravity at the high energy regime, namely during the emission process? Yeah, and then this effect can be cumulative during the propagation of the gravitational wave. And can this be detected on Earth, or is it difficult to do that?
sorry, the first question is whether you can have a modification during the emission and that modification grows during propagation. Is that the first question?
Right.
Or, sorry, versus can we have modifications during emission and separately modifications during propagation?
No, let us assume that it is only a modification during emission and not during the propagation.
Okay.
And then we have this cumulative effect during the propagation, or not? Is it?
Normally, no, you won't have. So basically, like in general relativity, this is the equation of motion of general relativity during propagation, and all the waves are going to propagate equally. So if you have some, I don't know, 10% of distortion deviation from GR in the initial condition here, you would expect to have the same amount, kind of the same percentage of distortion at reception. It wouldn't be a cumulative process.
Excellent, excellent. Yeah.
So that's why I wanted, like, that's precisely the point that I wanted to emphasize.
Excellent. I understood that. But then, is it possible to measure a modification of gravity during the production of gravitational waves, during the emission, I mean?
Yes. So if you see, for example, a certain pattern, like all the events exhibit some deviation from general relativity. So in general relativity, we know exactly what the strain as a function of time should be. So you can always, that's precisely what we do. We compare that to our signal. And if you start seeing that all of the events exhibit a certain and the same amount of distortion from general relativity, you would detect it. And people do exactly the same that I'm doing here, but for the emission. So you assume that the emitted wave has some free parameters. In the emission process, you include some free parameters that could describe possible deviations. And then you propagate that to see what you would observe. And you compare that to data. So it's a very similar process and it could definitely be detected.
Excellent. Thank you, Macarena.
Yes. Okay. So another effect is if we have another tensorial field interacting and it's going to have this extra field, a couple equation of motion to H. So this couple set of equations of motion, we can write them in this matrix form. So H is our gravitational wave field, and here I have added some extra field that I just call S. And this is the matrix form of the equation of motion, where for simplicity and for practical reasons and to fit observations, I'm assuming that here in the second time derivative and this k² term, the matrices here are some identity matrices are diagonal, so they do not interact through these second order derivatives. You could definitely change this assumption and work out what you get, but observations suggest that they probably don't interact at second order, but you could introduce some non-diagonal matrices at lower derivative orders, like first temporal derivatives or some linear term in K, or some non-derivative interaction here. So these are the blue terms that I'm putting here. And there are examples of specific modified gravity theories that can lead to any of these blue matrices that are non-diagonal. Here, I want to continue with the more common example of massive gravity. So I want to focus on this one, just for concreteness, but you can actually look at our paper that is on arXiv if you're interested in the other cases, but let's just focus on this mass matrix. So this mass matrix is going to appear if some non-diagonal mass matrix if the two tensorial fields interact through some non-derivative terms, like some potential that makes gravity interact with this extra-tensorial field. And a specific example of modified gravity theory that does that is the so-called massive by gravity theory, which is a two-metric theory. So we have the space-time metric G mu nu plus another, rank 2 tensor, another metric. And this theory propagates one massive and one massless graviton. And the two metrics interact only through a potential. But in any case, regardless of the type of interactions that these two fields have, the main difficulty is that these equations of motion are not exactly diagonalizable. So, when you want to solve them, that's the first difficulty that you encounter. However, you can make some approximations, which is the WKB, that we're going to assume that the frequency of the waves is much larger than the cosmological time, which is indeed the case for the gravitational waves from astrophysical sources that we're going to be detecting in the coming years and even in the next decade. So in this approximation of the high frequency limit, you can approximately diagonalize this equation and obtain two decoupled equations. And these two decoupled equations are going to describe the propagation of what we call the eigenstates, or doing some analogy with massive neutrinos, they're going to describe the mass eigenstates of this theory. But then the actual detected gravitational wave is going to be a linear combination of these eigenstates. So this is very analogous to neutrino oscillations. What you observe is going to be a linear combination of these eigenstates that oscillate and exchange energy between them. So this is the same thing that will happen. So in general, we can write H as a linear combination of the propagating eigenstates, and that's what we do here. So I know it's an ugly equation, but for now, the main message is the detected gravitational wave is going to be given by some initial condition that I'm going to assume that is given by general relativity. There's no emission modification, times the square bracket where I'm including all the modifications during propagation due to this extra interacting field. And in this case, because I only have two fields, there will be two eigenstates that are described here. This is the first. This is describing the contribution from the first eigenstate, and this is from the second one. And in general, we can see that they will induce deviations from general relativity here on H. One, through this phase, through this complex exponential here, that is what we call a phase modification of your signal. And that happens whenever these eigenstates have a modified dispersion relation compared to general relativity. So here this delta omega is the omega, the dispersion relation of the eigenstates, minus the dispersion relation in general relativity. If there's any modification, then there's going to be some phase here distortion. Then we have these functions f that have to do with the amplitude of these eigenstates. They could have some non-trivial modified amplitude that will affect the overall amplitude of the gravitational wave signal. And finally, one mathematically simple thing, but it's very physically important that I want to emphasize, is the fact that here we have a plus. And that means that these two eigenstates are going to actually interfere with each other. So as I said before, for gravitational waves, we measure the entire shape and the locations of peaks and troughs exactly as a function of time. So the absolute value of the phase of the wave is something observable, and effects such as interference between the two eigenstates, sometimes they could be out of phase and you detect nothing, or they could be in the same phase and you could detect a large gravitational wave. So those effects are going to be important and simply come here from this addition term. So I'm going to show you an explicit example, the case of massive by gravity. So we have two fields, my two tensorial fields, and they only interact through some mass matrix that I have added here. There's no other interaction. And in this particular theory, in the well-known theory of massive by gravity, typically the mass matrix satisfies this condition on the parameters. So I'm going to assume that, but that's not, that's nothing special. So in this case, what is the gravitational wave signal going to look like? So as I said, H is going to be given by some initial condition that is here, and this is the contribution from the eigenstates. This is the first eigenstate. If you remember, I told you that massive by gravity propagates one massless graviton and one massive graviton. And this is the eigenstate of the massless graviton because it has no phase correction. It has no modified dispersion relation. It propagates in the same way as general relativity. Whereas here we have the contribution from the second eigenstate that has a modified dispersion relation that is given by a massive graviton. So something very important that I will emphasize later, and I already mentioned before, is that a massive graviton doesn't propagate at the speed of light, it propagates slower. So in this case, where the gravitational waves are a signal, the total is a superposition of one gravitational wave that is describing a massless graviton and propagates at the speed of light, and another gravitational wave propagating slower than the speed of light. As these waves, these two eigenstates propagate together, one is going to start lagging behind because it's propagating slower than the other one. And we could even see the two eigenstates detect them separately at different times. I'm going to show you an example, an explicit plot for that. But this is like mathematically, at least, where all these observational effects are gonna be coming from. In this example, all the modifications from general relativity are described by two parameters, theta, that describes the relative amplitude of the two eigenstates, and m, which is the mass of the graviton of the second eigenstate. And we can recover general relativity, for example, when theta is equal to 0, so the contribution of the massive graviton vanishes, or when the mass is equal to 0 in this case. So both waves propagate like in GR and they add up and you don't see anything special.
Macarena?
Yes.
Do you know how these equations modify if you consider instead of massive gravitons, for instance, fermions? I don't know. I don't know. I'm thinking of a gravitational wave traveling across dark matter, for instance, assuming that matter has some sort of spin or whatever. Is there any calculation? Do you know anything about it?
So, okay, I can I guess say a couple of things. One is that here we are considering waves propagating on a perfectly homogeneous anisotropic universe. And when we have that simplification, then gravitational waves are only going to couple to tensorial degrees of freedom. So if you have, for example, interactions with an extrascalar field, then they won't interact with each other. Or a vector field, they won't interact. It has to be some tensorial degree of freedom. But people have also studied propagation through an inhomogeneous background. Like if you encounter a galaxy and you have some lensing effect, and in that case, the propagation is going to be, much more complicated, and gravitational waves can interact with a particle or a degree of freedom of any spin. And people have worked out the simple cases of an additional scalar field. I don't think anybody has calculated something for a spinor.
I see, thank you. But you can still have a matter without breaking the cosmological principles.
Yes, so here I am assuming that matter, or if you include dark matter there, is coupled minimally to the metric in the same way as general relativity. You could, I guess, modify that if you want, maybe only for dark matter, like only modify that because you don't want to modify how gravity interacts with other things. But yeah, I think you could do that, but I don't know, I haven't seen much about that explicitly.
We can discuss about it later. I mean,
yes, yeah, we can talk more about
thank you.
Okay. Okay, so I want to show you now the plots, the results of how the gravitational wave signal of this massive bigravity theory looks like. So again, we have the strain that is called h as a function of time in all these panels. This is, again, the gravitational wave signal of two equal mass black holes merging. And in gray, we have what we would see in GR. And in blue, we have the modified signal. And the only difference between all these panels, the four, is that we changed the distance at which the source is located. So this is a redshift. So as we go down here in the panels, the source is located further and further away. And as I said before, that means that it propagates for a longer amount of time and it suffers more and more distortions. So we do observe different things for the same source, but we only change the time of the duration of propagation. So let's start with the top one, which is if we have a source that is very close to us. And in this case, we have put a mass of, 10 to the minus 21, which is pretty large, but it's just to emphasize visually the effects. So this is the mass of the massive graviton that massive bigravity propagates. So for a very nearby source, we detect blue. And if we compare with gray, with general relativity, we see that there is this amplitude modulation. And this stage is what we call the coherence regime, because both eigenstates, the massless and massive graviton signals, are propagating together, superposing each other, and as a consequence of that, showing some interference effects. And these interference effects is what causes this amplitude modulation. And this is what I show here. So in orange, we have the first eigenstates, that is the signal of the massless graviton. And in green, we have the second eigenstate of the massive graviton. And just because they have that different dispersion relation, they look different. And sometimes, like for example here, both eigenstates are in phase, but at other times, like around here, they are out of phase. So this is what causes this amplitude modulation. It's just an interference effect. But if the source is at higher redshift, like in this second panel, we can see here that the signal of the massive graviton is starting to lag behind because it propagates slower than the speed of light, whereas orange propagates at the speed of light. So the net signal looks some kind of mess like this. But if the redshift is even larger, then we start seeing the initial formation of what we call echoes, which means that we can start detecting separately each eigenstate because they have decohered. So here we have the first propagating eigenstate, and here we have the second one. So this is the part of the mass, this is a contribution of the massless graviton, and this is the massive graviton. And for an even higher redshift, we can see a clear temporal separation between the two signals in this case. And as you can see, this first signal, the first echo that we would detect, looks exactly like general relativity, but with a different amplitude, because part of the energy is in the massive graviton contribution in the second eigenstate, and only a fraction of the total energy is in the massless graviton eigenstate. So it has the same phase evolution, no distortion, just a different amplitude, but then you would detect an echo, a signal, in this case, a few seconds or fractions of seconds later, which in this case would be very distorted and deformed because it had a modified dispersion relation that corresponds to the massive graviton case. So here I'm trying to illustrate the various effects that you could get when you have interactions. So you could change the amplitude, then the overall amplitude, you could introduce amplitude modulations, and even observe multiple echoes of your signal. So here's just a summary of the main results. So gravitational waves allow us to probe cosmological fields if they interact non-trivially with gravity. And in particular, gravitation waves may interact with tensor degrees of freedom. And something that I try to emphasize is that all the distortions caused during propagation accumulate over time. So further future gravitation wave detectors, like the ones that we're going to have in a decade, are going to observe sources, as I said, at redshift 10 or even 20, like when the first stars formed, and are going to put very strong constraints on all these propagation modifications. And some example of effects, observable effects that I mentioned, is some amplitude modulations, some changes in the phase evolution, and even the formation of echoes. And currently, we don't see any echoes or anything like that. So again, for this massive by gravity model, we should be able to impose constraints even with the current gravitational wave events. And that's something that we will be thinking of doing in the future. But thank you.
Thank you very much, Macarena, for the very nice seminar talk. Are there questions from the audience?
I have perhaps the last one, and thank you, Macarena, for your very nice and clear presentation. It was really, really, really nice to hear you. So at the end of the day, regarding the phenomenology that you were presenting today, which modified gravity you think that it is still allowed by observations?
I think there is a bit of a philosophical ingredient in that answer, in the sense that in this case, for example, if we have an extra field that is interacting with gravity, you can always start making the interaction parameter between the extra field and gravity smaller and smaller to always agree with data. And we eventually need to ask ourselves this maybe subjective questions of when to stop. I mean, when are the constraints are going to be enough so that we truly believe that there are no additional modifications. So, but I think in general, if you have a model that all the new coming data starts telling you that your interaction parameter has to be smaller and smaller and smaller, definitely that's something that that's very unattractive, and maybe you're not gaining anything by analyzing that model compared to Lambda CDM. So, I mean, I don't know, I don't know a specific model. I don't have like a specific model in mind. I think for now, many complicated models have been discarded by the data, and now mostly you can have like a scalar field, like during inflation, like a simple scalar field with some potential that leads to some accelerated expansion of the universe. Things like that are definitely viable for now.
I see, but what about the future observations? Can this be used in order to rule out some of the modified gravity models? I agree with you that perhaps we can constrain a lot the parameters, but there still be a chance such that there is a window in which the parameters can still be allowed, super constrained, of course, but they are still allowed. But what if future observations allow us to eventually rule out the data? Do you know if these observations can do that?
Yeah, I mean, if your specific theory makes, a very specific prediction, like for example, I mean, not regarding dark energy, but there are, for example, inflationary models that predict that there is no primordial gravitational wave emission at all. So if you ever detect some primordial gravitational wave emission, from example, from the cosmic microwave background or future gravitational wave detectors, then you can definitely discard those very specific, predictions that some of the models make. So the model needs to have, if it has a feature like that, like a very clear, non-trivial prediction, you can rule out that. But many of the models, sometimes they don't make predictions like that, and they can be tuned to look very similar to Lambda CDM.
I see. Thank you very much.
So are there any other questions from the audience?
I
have
a
a question.
Carlos Sandenomar.
Okay.
Thank you. Well, in first place, thank you so much, Macarena, for offer us this important and interesting issue. So I have a question about well, I understood this work reveals the presence of cosmological fields. What about those cosmological fields? It's a kind of particles, but I don't know, because, for example, that cosmological fields must be able to interact with.
To have other consequences, you mean?
Yeah. Because
yes.
Well, when you have a work which it shows there's another extra ingredient, it is natural to ask, what about that ingredient? What about these cosmological fields? Well, it's not related. I think it's not related with inflation, because as you said, cosmological wave, the modes from the inflation, it doesn't matter.
Yes.
It doesn't matter today. It was,
I agree. Yes.
Yeah.
In my case, I was thinking of a dark energy particle, mostly. Like, we have an extra field that describes a fundamental particle associated to dark energy. And this field interacts with gravity. And indeed, like if you write the full modified gravity theory, there are going to be other consequences of the presence of this field. Like it's going to, for example, typically it will change how galaxies, for example, cluster, how fast they cluster. And that's something that can be constrained with galaxy surveys. And for example, I mentioned, I don't know why I can go back, but here, this alpha m parameter, that this modification, for example, can appear when you have this fundamental scalar dark energy particle. And this paper uses precisely cosmic microwave background and galaxy survey data, because this dark energy particle affects, as I was saying, the cluster of galaxies. It can affect, as a consequence of affecting the cluster of galaxies, it affects, for example, how the cosmic microwave background is lensed by these galaxies and various features like that. And that gives you constraint, but not the strongest constraints. So the strongest constraints you get when you combine both gravitational wave and electromagnetic data. So the additional cosmological consequences of these fields are not incompatible with observations, with electromagnetic observations.
So that particles can be able to interact with gravitational waves?
The dark energy particle, yes, I'm assuming here that it interacts with gravity. So yeah, so I don't know if you have heard of Horndeski theories, for example. So these are modified gravities where you have one extra scalar field.
Yeah,
and
I did.
Yeah, precisely in these Horndeski theories, the scalar field interacts with gravitational waves.
Good.
And that's what it leads to this alpha m.
Right.
Okay, I don't know whether that answers completely your question.
No, it's yeah, yeah, I got it. Thank you.
Okay.
Omar?
Thank you. Well, it's just a short question. It seems to me that somehow you are hunting the mass of the graviton, right? So
in this talk, yes.
Yeah. So could you say that you can rule out this bimassive gravity?
If we could rule out a massive gravity, I think it is, again, you can always make the mass of the graviton smaller and smaller and smaller as you get data. Currently, if you combined all the predictions that a massive graviton could lead to, so here I only talked about how gravitation waves change with a massive graviton, but again, a massive graviton would affect a bunch of other observables, not only cosmologically, but also in the solar system. For example, you can get very strong constraints. If you have a massive graviton, it would change how, the gravitational profile of the force between planets. And for example, from Mercury's precession, you can get very strong constraints. Also, in galaxy observations, when people analyze the velocity rotations of objects in galaxies, that also gives very strong constraints. So far the data indicates, that the mass has to be smaller and smaller and smaller. And I think we're at the point in which, if you put all the observations together, it has to be of order 10 to the minus 33 electron volts, which basically means that it's just so small that it can only have some cosmological effect, but even that could be very marginal. For an even smaller mass, there will be no effect because you cannot probe such low energies. So yeah, I guess to answer your question, I would say yes, we are constraining these theories very well.
Good, thank you.
So I have two questions. So the main constraint, observational constraint that you have on the mass of the graviton, let's say, is the similarity of the speed of light with the detected speed of gravitational wave, right? That's the main constraint. Is that gravitational waves, like when you observe like the kilonova, you observe it in the optic and in the gravitational wave spectrum, and you observe that both signals arrive at the same time. That's the constraint essentially, right? So in this regard, you can think the following: if you have a theory with two metrics, you actually have like two gravitons, right? So you can separate the modes into the massless graviton and the massive graviton, but then the metric of the space-time in a way is the massless graviton, and the massive graviton just becomes a spin-2 field that propagates in this underlying space-time, right? So maybe like if you make this massive graviton, instead of making it marginally massive or very little mass, you take the other approach. You make it very massive. The time delay of the massive graviton propagation will be huge. So maybe then you wouldn't detect it because it will lag too much behind the massless wave. So let's say you measure, right? So you detect the gravitational wave, but then the gravitational wave that you detect, you interpret it correctly as the massless graviton, okay? But then you may miss the massive graviton because it may have a very large time delay. So actually, maybe like another way that I imagine, maybe not, this is what I'm asking, right? That you could think of bypassing the observational constraint, not by making the mass of the massive graviton mode very small, or like, in this case, like modifying the dispersion relation with this with this mass parameter, making it very small, but actually by considering that you have more than one graviton mode and making the massive one very massive, so that you actually don't detect it, or that it lags behind so much that you don't interpret it as part of the same signal, or that it gets like diluted on the way here, right? So what about this possibility? This is my first question, and the second one is that if you have a gravitational wave propagation with a speed smaller than the speed of light, you could imagine having a like gravitational Cherenkov effect, because essentially every particle in the universe couples through gravity, at least minimally. Well, in the models of modified gravity that you consider, you may have non-minimal couplings, right? But at least all matter couples minimally to gravity. So in this scenario, every field in existence is gravitationally charged, if you want to think it this way. So like any particle that travels faster than the graviton, but of course slower than the speed of light, would generate like the analog of gravitational Cherenkov effect. So could you measure this in principle? Like what kind of phenomena could this give rise to? Those are my two questions.
Yes. Okay, so for the first question, I think we would have like to formulate properly the model, but I think I would say that for an individual event, maybe you can bypass this extra modification by having a very large mass if it has a very large time delay. And I'm saying this because, as I was saying, the time delay, or how big the time delay is, will depend on how long has the signal been propagating for. So if you have, in fact, a source that is very far, the time delay could be very large, but then the next day you may detect a source that is much closer, and now maybe you will see some time delay. So in that sense, it's not obvious that you can always bypass all the observations by having a very large mass. And for your second question, I mentioned here this constraint on alpha T that I cited this paper that is from the LIGO-Virgo collaboration. And this constraint both the possibility of having alpha t positive, so a speed larger than c, and alpha t negative or smaller than c. And in either case, larger or smaller has to deviate from the speed of light by these 10 to minus 15 parts. And indeed, the lower bound, the negative, actually doesn't come from gravitational waves. It's only the upper bound. The lower bound comes from this gravitational Cherenkov radiation that people have already obtained by looking at very high energy particles, detecting high energy, astrophysical particles. And if they were emitting gravitational waves, then they would lose a lot of energy during their propagation. And the limit of 10 to the minus 15, the lower bound, you obtain using that. So the fact that we can detect very high energy cosmic particles means that they cannot be a huge amount of this gravitational Cherenkov radiation.
Okay, thank you. Are there any other questions from the audience?
I have perhaps a very brief question. So this is analogous to the case of the mass of the photon, right? So we have experiments that constrain the mass of the photon to be very, very slow, but it is different in principle from zero. But we know from gauge invariance that there are theoretical problems in this case. And I was wondering about, as an analogous in massive gravity, is there any problem, for instance, with diffeomorphism invariance or any other gauge invariance in gravity regarding the mass of the graviton in this case?
Yes, yes, indeed, if you write down the full nonlinear theory of a massive graviton, it wouldn't have general diffeomorphism invariance. But basically on an empty universe, or you could still have some Minkowski solution. But then in any non-trivial background, like a cosmological background, then you are going to have something different, basically. But in principle, there is nothing, there's no like observation that forbids that, in the sense that, as I was saying, like in complete flat space, you could not notice the fact, and you could not see any modification due to the mass. So I mean, the space-time would still be a Minkowski space that it has, fixed rotation and translation invariance. And I guess most of the observations that constrain, like Lorentz breaking symmetries, it comes from this flat space. So as I was saying, in principle, you do break general diffeomorphism invariance, but there's nothing fundamentally wrong with that.
Thank you, Macarena.
So, like regarding the same question, what happens when you have like two metrics, and let's say, okay, you have two metrics and you can diagonalize the mass metric for just for the free gravitational part, right? Then you just, I mean, you can interpret the zero mass eigenvalue of the mass matrix of the gravitational part as your space-time, and then the massive part as just a spin 2 tensor that propagates on the space-time. So in this case, I think the problem is resolved, right? I mean, I'm not sure, but I think it is, right? Like you say, okay, if I have like two metrics, I interpret one as a mass, a real, like a true massless graviton, and then the other one is just a spin 2 field. And then you say, I just lower and raise indices with the massless graviton. And I think then you don't have this problem.
Yes, I agree.
Right.
However, in the typical massive by gravity theory that I was mentioning, that is called DRGT by the, in the initials of the authors, the space-time metric is not the one associated to the massless graviton. It's a linear combination. So that's why precisely here in my plots, I always have that the gravitational waves, the observed ones, are a combination of both. So in that theory where you have two metrics, you could have two copies of diffeomorphism invariance, but you only have one in this massive by gravity.
I see. Good, thank you. So are there further questions?
Last one.
Yes, Carlos, go ahead.
Thank you. Are you assuming the tensor speed excess alpha t is almost constant? Its variation is so slow because I think that equation you use Fourier space, right? So this is the equation for the one mode who has wave number k, right?
Yes,
so
a monochromatic wave. Yeah.
Good. So I remember when I studied that the term who multiplies to HP must be constants, right?
This alpha t could be a constant, but it doesn't need to be a constant. Because in our case, we are doing perturbation theory around an expanding universe. The first thing that could appear is a cosmological time evolution in this alpha t, in which case this constraint would still be valid, but only to constrain the very late time evolution, because these constraints come from observations of nearby objects. So only at late times this constraint would be valid. In principle, you don't know what's happening at further distances. So that's one modification. As I said, it comes because we are assuming that our background is expanding. So there's no requirement for this to be a constant.
So it can vary slowly or not.
Yeah, it's slowly compared to the period of the wave. So it evolves on cosmological times, and here I'm always assuming that the period of the wave is shorter. Yes, some slow variation.
So are there any further questions? No, if not, let's thank Macarena Lagos again for the excellent seminar.
Thank you for having me and showing so much interest in this.
Thank you.